Industrial hydraulic systems often require more precise pressure control than simple pressure control valves are able to provide. When greater control is needed, pilot-operated pressure control valves are frequently used. Unlike the direct and remotely operated pressure control valves we saw in the last lesson, these pilot-operated valves use a second valve, pilot valve, to control the operation of the main valve. Though the schematic symbol indicates two physically separate valves are used, these pilot-operated valves actually combine the pilot valve and the main valve in a single valve body. The pressure control valves we've seen so far have their spools biased by springs. When the tension force of the spring is overcome by fluid pressure, the valve spool moves, changing the state of the valve. However, the pressure at which the spool first begins to move, the cracking pressure, is less than the pressure at which the valve is set. For example, a valve set at 1,000 psi may pass 10 gallons per minute at that pressure. However, it might crack open at 800 psi, then pass more and more fluid until it reaches full flow at 1,000 psi. In addition to early cracking pressures, the pressure control valves we saw earlier also have high override characteristics. That means if flow through the valve increases beyond 10 GPM, pressure will rise above or override the 1,000 psi setting on the valve. Both cracking pressure and override are shown on this graph. The valve starts passing flow at about 800 psi, then increases as pressure rises. If system pressure rises above 1,000 psi, flow through the valve will increase to more than 10 GPM. Hydraulic systems would operate more efficiently if valve spools remained seated until the rated pressure was reached. At the rated pressure, the valve should quickly change from its normal state to its operating state and stay there. This would allow pressure to be controlled with greater precision. Pilot operation of pressure control valves improves the performance of the valve. It uses pilot pressure and pressure from a bias spring to keep the spool of the main valve in its normal position, passing or non-passing, until a preset pressure is reached. Pressure developed by the pilot valve stabilizes pressure at the main valve spool. As a result, both early cracking pressure and high override are reduced to a minimum. To understand more clearly how pilot-operated pressure control valves work, let's take a close look at a pilot-operated relief valve. In a pilot-operated relief valve, the main valve spool is biased by a light spring with a tension of about 25 psi, which holds the tapered stem of the spool in the valve's outlet to tank. Fluid at system pressure pushes against the underside of the spool and passes through an orifice. The spool in the pilot valve is a dart with a relatively small area exposed to pressure and a relatively stiff spring. The dart spring in this valve, for example, has a tension value of 975 psi, so it remains seated until pilot pressure at the face of the dart reaches 975 psi. Suppose the valve is set at 1,000 psi. If system pressure rises to 900 psi, nothing happens. The main valve does not open because pilot pressure through the orifice and the tension of the 25 psi bias spring keep the spool non-passing. The pilot valve stays closed because 900 psi isn't enough to make the dart passing. However, at 990 psi, the pilot dart opens, but the main valve remains closed. That's because even though 990 psi pushes up on the spool, there is 1,000 psi pushing down on the spool. The 1,000 psi is the combination of the 975 psi pilot pressure at the pilot dart and the 25 psi from the bias spring in the main valve. Finally, when the system pressure reaches 1,000 psi, the main valve spool opens. Since cracking of the main valve typically begins somewhere above 995 psi, the valve changes from completely closed to fully open with very little pressure differential. If we plot the performance of the valve on a graph, it closely follows the dotted line, which indicates the ideal condition. No flow at all is passed until 975 psi. At 1000 psi, with very little rise in pressure, the valve allows full flow. Many different types of pressure control valves can be pilot operated in a similar way. For example, sequence valves, counterbalance valves, and reducing valves are all frequently pilot operated. The biggest difference is usually the spool. Although the main spools in these valves differ from the spool used in a relief valve, the basic operation is the same. That is, the pilot valve returns fluid to tank, reducing pressure on one side of the main valve spool, allowing it to shift in response to system pressure. Very often it's desirable to adjust a valve from a remote location. Since operation of the main valve depends on when its pilot valve returns to tank, a second pilot valve can be used to adjust the pressure at which returning will occur. As long as the pressure setting of the second pilot valve is lower than the setting of the first pilot valve, the second pilot valve will determine when the main valve opens. Erratic operation of pilot-operated pressure control valves can be caused by wear, by dirt, and by remote pilot lines that are too long. Wear often occurs when the pilot dart moves on and off its seat. If this wear becomes excessive, fluid may leak from the main spring chamber back to tank. This can lead to insufficient pilot pressure above the spool, and the valve may not operate properly. Erratic operation may also occur when the small orifices in spools become plugged by dirt in contaminated fluid. Finally, long lines between the remote pilot valve and the main valve can cause pressure pulsations and excessive vibration. These lines should always be kept as short as possible, and they should be made of stiff tubing or pipe. In an earlier lesson, we saw how a differential unloading relief valve can conserve horsepower by unloading a pump to tank after an accumulator has been charged. Pilot-operated relief valves can be used in the same way. If the pilot valve section is vented, the main valve will pass flow at a very low pressure, the tension pressure of the spring biasing the main valve. In this valve, for example, the tension pressure of the bias spring is only 25 psi, so the valve returns to tank as soon as the pilot valve is vented. Usually, a solenoid-operated valve is used to vent the pilot valve. Whenever the solenoid is energized, system pressure has to overcome only the tension pressure of the light bias spring. Fluid returns to tank at a very low pressure. The pressure at which the system unloads is determined by the tension pressure of the main valve's bias spring. A light tension spring offers little resistance to flow being returned to tank and is called a low vent spring. A high vent spring is a heavier spring that creates more resistance but will operate more quickly. While the vented pilot-operated relief valve in this circuit allows us to unload the pump while the system isn't working, it's sometimes useful to unload part of the system while work is being done. This is often done with a high-low system using two pumps. In this circuit, for example, we have a 45 GPM pump and a 5 GPM pump. With both pumps operating, the actuator will advance toward the load rapidly and at low pressure with 50 GPM total flow. Once the actuator meets the resistance at the load, pressure rises. If the unloading valve is set at 500 psi, the large pump will return to tank when pressure gets to that point. A check valve prevents the small pump from unloading, so it continues to supply 5 GPM at a pressure that rises to the setting of the relief valve, 1500 psi. When the extension or work stroke is completed and the return stroke starts, pressure drops below 500 psi. The unloading valve closes, the flow from the large pump is once again directed into the system, and the actuator returns very quickly. Another type of pressure control valve that can be used to operate a system more efficiently is a solenoid-operated relief valve. This valve includes a pilot-operated relief valve, a solenoid-controlled spring offset directional control valve, and a remote pilot valve. In this example, the remote pilot valve is set to open at 900 psi, while the main pilot valve is set for 1500 psi. As long as the remote pilot valve remains connected, it controls the operation of the main valve. If the remote pilot is disconnected, the other pilot valve determines the pressure at which the relief valve becomes passing. The remote pilot can be connected and disconnected by the directional control valve. When the solenoid on the directional control valve is de-energized, the remote pilot valve is disconnected from the main valve, and maximum system pressure is limited to the 1500 psi setting of the main pilot valve. When the solenoid is energized and the remote pilot valve is connected to the main valve, the maximum system pressure is limited to the 900 psi setting of the remote valve. Now, let's see how a solenoid-operated relief valve is used in a circuit. Cylinder A requires a flow of 10 GPM at 1300 psi to move its load, while cylinder B needs only 6 GPM at 700 psi. The pump produces an additional 100 psi to overcome liquid resistance. The simple relief valve is set to open at 1500 psi. When the directional control valve sends pump flow to cylinder A, the horsepower used by the cylinder to do work and the horsepower produced by the pump are pretty evenly matched. We learned in an earlier lesson that horsepower can be calculated by multiplying GPM by PSI by the constant 0.000583. That means that the horsepower used by cylinder A equals 10 times 1300 times 0.000583, or a little less than 7.6 horsepower. The pump is generating 10 times 1400 times 0.000583, or a little less than 8.2 horsepower. However, when we shift the pump flow to cylinder B, the system becomes quite a bit less efficient. The pressure-compensated flow control valve lets only 6 GPM pass at 700 psi. This means cylinder B is using only 6 times 700 times 0.000583, or about 2.4 horsepower, while the pump is producing about 8.7 horsepower to push the remaining 4 GPM past the relief valve at 1500 psi. This excess horsepower is turned into heat in the system. By installing a solenoid-operated relief valve, the system can be made to operate more efficiently. Now, when cylinder A completes its work, the solenoid on the relief valve energizes, connecting the remote pilot valve. That limits the system pressure to 900 psi. Therefore, the pump uses only about 5.2 horsepower when cylinder B is working instead of the previous 8.7 horsepower. That means the pump will be generating less heat in the system. As we've seen, there are several ways to reduce the amount of power and heat generated when the system is not working, or when the work being done decreases. We can direct pump flow to tank at low pressure using vented pilot-operated relief valves. We can use unloading valves in a high-low circuit, and we can use directional control valves to select different pilot relief settings. However, there are limits on how much horsepower can be conserved and still keep the system operating. Just because a pump's flow is directed to tank at low pressure doesn't mean the pump's prime mover, usually an electric motor, no longer has to work. How much work the motor has to do when the pump is idling depends upon the pump's overall efficiency. Pump efficiency can be determined by dividing the pump's hydraulic horsepower by the input horsepower of the electric motor, and then multiplying that number by 100. For instance, suppose a pump is delivering 10 GPM at 1000 psi. This would be about 5.8 horsepower. If the electric motor has to develop 7 horsepower to turn the pump at that speed, then the pump's overall efficiency would be 5.8. The horsepower of the pump divided by 7, the horsepower of the motor times 100, or about 83%. In this lesson, we have seen how pilot-operated relief valves work and how they can be used in hydraulic systems. In the next lesson, we'll take a look at different types of hydraulic pumps and see how they work.